Hello and welcome to the video lecture series on contact mechanics in the course M7033T Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work at the Division of Machine Elements here at Luleå University of Technology. Now this is the first introduction part of the first video lecture on contact mechanics fundamentals. The theoretical foundation for the material presented in this video lectures may be found in the course compendium. And if you want to take a deeper look in details of contact mechanics, I suggest you to look into K.L. Johnson's book Contact Mechanics from 1984. So this is the outline of this video lecture. So in part 1, I'm going to introduce you to the contact mechanics problem and then successively build up the fundamentals of the half-space theory in the next part, introduce you to the complementarity problem in the third part, and then have a brief look into what happens underneath the surface, what happens if we add friction and roughness to a seemingly smooth contact. Then part 5 is a bit more on the mathematical aspects, and it's devoted to defining independent variables and input parameters of the problem. And this is because in part 6 we are going to carry out the non-dimensionalization of the contact mechanics problem, and then we need this. And after that we will pay some time to the Hertzian problem and its solution, because it's important as it's an analytical solution. There is also another analytical solution, the Westergaard solution, which I deem as equally important, and it also reflects that the contact mechanics problem or the contact mechanics model that we develop here can be applied to study also rough surfaces in contact with each other. And the last part is a note on the deflection, elastic deformation in 2D, and that will be all for this video lecture. So in contact mechanics we want to study, for example, how the contacting bodies deforms, and what we see here in this window is the upper boundary of the lower body, which we will bring into contact with this lower boundary of the upper body. And we have here the gap between the surfaces, and we will see later on it will play a very important role in the modeling, and we will denote this gap by H in the remainder of this course. What we should also pay attention to here in this picture is the scale. And we can clearly see there's a 1,000 times magnification here on the y-axis, which is in micrometer, while the x-axis is in millimeter. And this is necessary, of course, for us to be able to see what the surface looks like. Otherwise, if the scale was 1:1, they would appear very, very plain. We note that we now have brought these two bodies into contact in just a single point here. And we will now see what happens if we load these bodies and pressing them against each other. So here's an animation for this. So we can see as we increase the load, the surfaces comply and deform against each other, and then we start to slide, and the actual real contact between the surfaces moves over different places of the surfaces as they move relative to each other. Needless to say, it's very important to also study the associated stresses that develops, and in this window we will soon see the normal stress developing as we load the surfaces together. So they only touch each other here at this initial contact point, and therefore we can only see a small thing, a small notch here on the x-axis of the pressure window. But let's see what happens when we start the animation. So we load the surfaces together, and as you saw, the stresses were developing up to a certain point, and then after this point we start to slide the surfaces relative to each other, and the contacting patches, they move, of course, and so does the associated contact pressure. Let us now have a more detailed look what happens in the contact between these two asperities, as we call them. We can model these two asperities as circular bodies, cylindrical bodies. And of course they may have different material properties here, with different Young's modulus and different Poisson ratios. When the surfaces are loaded against each other, they make contact, and we are interested in how to model this contact mechanics and how to solve that problem numerically. There are mainly two different methods to use here, and the first one is the finite element method, and this one solves the solid mechanics equations in 3D and with the appropriate boundary conditions and with some specific method, typically penalty-based method for the contact. It requires a full 3D mesh, and that will render, of course, a vast number of degrees of freedoms. And imagine if you have to account for the surface roughness also, then it will be tremendously many boundary elements required for this one. The other main branch of methods are the boundary element based methods, and these are dimension reduced models. So 3D, the full 3D model goes to 2D, 2D goes to 1D, which of course makes it a lot less computational heavy, and therefore they may be practical to use when you have, for example, surface roughness to consider. The boundary element methods, they are typically based on this half-space theory, and assumptions required for a half-space theory to be applicable is that the influence of the boundaries of the bodies is negligible. So the bodies are actually half spaces, and the surfaces must make small slopes. So if we, already at the left schematic here of contact, we see that the surfaces have small slopes, but even when we are magnifying the portion where it makes contact here, we can see that the slopes are very, very small, and this is a basic requirement for this half-space theory to work. Then one has to remember that when we visualize surface roughness, we typically blow up the height scale 1,000 times or so to see the roughness itself, and it is actually quite smooth. The slopes are quite small for typical engineering surfaces.